So for this next bit of the section, now that we're comfortable with this notion of what it means to simplify radicals, we're going to start talking about operations on radicals. So today we're really going to focus on what it means to add and subtract radicals. Now the neat thing is that addition and subtraction of radicals works the same way in terms of how we regard, in terms of how we define addition and subtraction of polynomials. So you guys remember in polynomials, we said that to combine polynomial terms together, that we had to have like terms. And that like terms means we have the same base and we also have the same exponent stuck on that base. Well, how does this relate to radicals? Well, in radical form, instead of saying we have the same base and the same exponents, in radical form, we say we can combine them together when we have the same radicand and the same index. So assuming that these guys are the same, assuming that we want to combine a bunch of stuff together and we have the same index and the same radicand, we can combine them. Now remember, with polynomials, let's take a look over here at what combining looks like in polynomial form and what combining looks like in radical form. In polynomials, we have 13x minus 7x plus 5x. And if I were to ask you to combine these, you would say, I can combine them because the base and exponent are the same in all of them, right? They all have x to the first power. 13 minus 7 is 6, and 6 plus 5 gives us 11. So this is equivalent to saying 11x. Remember that the base and exponent don't change. It's exactly the same thing in radical form. When we go to combine these, I'd say, okay, well, this is the square root of x, this is the square root of x, this is the square root of x. So all of the radicands are the same. They all have an x. And notice too that they all have the same index. There's all a little hidden 2 over here. So that means we're going to be left with the square root of x. Well, how many of them? Then we just use the coefficients to tell us how many of them we have altogether. 13 minus 7 is 6, and 6 plus 5 is 11. So this is the same thing as saying 11 square root of x. So again, addition and subtraction of radicals is exactly the same as addition and subtraction of polynomials. You guys are familiar with polynomial addition and subtraction as well. So we're looking for the same base and exponent in polynomials. We're looking for the same radicand and the same index when we're dealing with radicals. So let's get into some radical examples. Let's take a look at question number 1. Okay, question number 1 says, combine and simplify completely. Well, before we do that, what I want to make sure that you can do is just understand which one of these guys are considered to be like terms. Let's highlight the like terms. So let's take a look at the square root of a. What can we combine with this guy? Well, we can combine other square roots of a's. Do we see any other square roots of a's? So this guy, notice the radicand's the same, but the index isn't. So we can't combine them together. This is the cube root of a. It's different than the square root of a. This guy is a b, so the radicand's different, so we can't combine them. Oh, here we go. We have another square root of a over here. So we can combine these two terms together. Cube root of b is not the same as the square root of a. Cube root of a is not the same as the square root of a. So when we go to combine these guys together, we have 5 square root of a plus 3 square root of a, and that's going to give us 8 square root of a's, right? If you have 5 of something, you add 3 onto it, you're going to have 8 of them all together. Now let's look at other possibilities. Let's look at the cube root of a. Do we have any other cube root of a terms? Remember, you have to have the same radicand and the same index to combine them. No, that's the square root of b, so the radicands are different. That's b as well, so the radicands are different. Look at that, we have a cube root of a. So we have 6 cube root of a's minus cube root of a. Remember, there's a little hidden 1. If you don't see a coefficient, it's assumed to be a 1. So you have 6 of something, you take away 1 of something, and then we're going to be left with 5 of that thing. So that's plus 5 cube root of a. And what are we left with? Well, let's take a look at this. We have the square root of b. Do we have any other square root of b's? Well, no, that's a cube root of b. So we don't have any other square root of b. So we're just going to rewrite that term. That's minus 2 square root of b. And then our last term, minus 7 cube root of b. There's no other cube root of b term, so we're just going to call that last term minus 7 cube root of b. So again, these guys work just like polynomials do. In fact, if you want to think about these in terms of being in polynomial form, we could do something like this. We could call this 5a squared plus 6a cubed minus 2b squared plus 3a squared minus 7b cubed minus a cubed. And so if you think about it like this, and I'm just making this up, I'm just trying to show you what the equivalent form for polynomials would look like. 5a squared plus 3a squared gives us 8a squared. 6a cubed minus 1a cubed gives us 5a cubed. And then negative 2b squared, we can't combine anything with that. Negative 7b cubed, we can't combine anything with that, right? I hope you guys can see that, look, same structure. We might have, here we're dealing with square roots and here we're dealing with squared, right? So here we have rational exponents and here we have whole number exponents, but you get the general idea. So let's take a look at question, we're going to take a look at a handful of examples here. We have 6 examples to look at, but let's try question number 2. Here's what question number 2 says. We have the square root of 18 plus 3 square root of 50 minus 4 square root of 2. Well, when you go and look at this, I hope the first thing you say is, let me see if I can combine these guys. And I can't, because square root of 18 is a different radicand than square root of 50, which is a different radicand than square root of 2. So initially, we can't combine any of these. So the question is, well, why did I give you this question? What's the point of giving you a question that you can't do anything about? And the answer is this. What you want to do first is see if you can simplify the radicals. So once you simplify the radicals, then sometimes we're left with radicands that are the same and we can combine them. So this becomes a process when we talk about addition and subtraction of radicals, this becomes a process of making sure that you can simplify it first. So let's take a look at 18, the square root of 18. So for 18, what we're doing is we're looking for we're looking for a perfect square factor of 18. And look, we have one. A perfect square factor of 18 is 9. So I'm going to rewrite the square root of 18, the square root of 9 times the square root of 2. And that's the same thing as saying 3 times the square root of 2. Okay, well, what comes next? Let's take a look at 3 square root of 50. Same thing, we're going to say to ourselves, can we simplify the square root of 50? So we need to look for perfect square factors of 50. I have 1 and 50. I have 2 and 25. 3 doesn't go in, 4 doesn't go in, 5 goes in 10 times, 6, 7, 8, 9, nope, and then we're done. Any perfect square factors of 50? Take a look. We have 2 and 25. So this is going to be plus 3 square root of 50. We can rewrite that as the square root of 25 times the square root of 2. Remember, this term, I still have to bring it down. It's still part of that. So this becomes plus 3 times. Now the square root of 25 is 5 times the square root of 2. And we didn't talk about this. We're going to talk about this under multiplication and division, but we define addition and subtraction first for radicals. Numbers on the outside of the radicals are multiplied together, and numbers on the inside of the radical are multiplied together. So what that means is 3 times 5 is the same thing as saying 15 square root of 2. Okay, and then let's take a look at that last guy, minus 4 square root of 2. Well, 2 is prime, so we can't do anything to simplify it, so I'm just going to bring it on down, and now we have minus 4 square root of 2. Take a look. Now let's look for like terms. Now let's look for like terms in terms of radicals. And I hope you can notice now we have like terms. We have a radicand of 2 in all of these guys. So we can combine them after we simplify them. Well, question we're going to say to ourselves is how many square root of 2's do we have? Well, 3 plus 15 is 18. 18 minus 4 is 14. So the answer to this first guy simplified completely is 14 times the square root of 2. Once again, the hint is when you're working under multiplication and subtraction, you really want to make sure that you simplify whatever's in the radical first. And that's simplifying what's in the radical. You'll see like terms will pop out once you're done simplifying them. So begin all of these when you guys are doing your homework. If they're not simplified, begin all of these addition and subtraction of radicals by simplifying them. All right, let's take a look in here. So again, I noticed first thing, I noticed that, look, these are not the same. We have 27, we have 16, we have 25. So they're cube roots of all of them, right? But so the index is the same, but the radicand is not. So that means we're going to try to simplify each one of these guys. So let's see what we can do. 5 times the cube root of 27. Well, 27 is a perfect cube, right? What number when you cube it gives us 27? Well, that's the same thing as saying 3. So this is equal to 5 times 3, and that is equal to 15. The cube root of 16. What number times itself 3 times gives us 16? Well, 16 is not a perfect cube, but we have to make sure that 16 doesn't have any factors that's a perfect cube when we're simplifying it. So I'm going to look for all of the factors of 16. I have 1, 16, 2, 8, 4, 4. Are any of these perfect cubes? Sure, 8's a perfect cube. So we can rewrite this as minus 3 times the cube root of 8 times the cube root of 2. And this becomes minus 3 times the cube root of 8 is 2 times the cube root of 2. So we get 15 minus, and 3 times 2 is 6, times the cube root of 2. All right, let's take a look at that last term, 8 times the cube root of 125. Here, so we'll call this plus 8, and then the cube root of 125. Is there a number, if we cube it, is there a number if we multiply it by itself 3 times that will give us 125? Yes, that number is 5. The cube root, 125 is a perfect cube because 5 cubed gives us 125. So that becomes plus 8 times 5, which is plus 40. So when we go to the simplified version of this, notice that we do have one pair of like terms. We have constant terms here, and these guys we can combine together. So 15 plus 40, that gives us 55 minus 6 times the cube root of 2. Now, can we combine these? I hope you said no. It's a little crack in the egg's head because you can't combine them. We can't combine them because they're not like terms. We have a cube root of 2 here, but we don't have a cube root of 2 here. So this would be that answer simplified completely. It's the same thing as saying 55 minus 6 times the cube root of 2. Okay, let's take a look at question number 4. Question number 4 is negative 3x times the square root of 12x plus 5 times the square root of 27x cubed minus 7x times the square root of 3x. Here's what we're going to do first. We're going to look inside each one of these radicals and see what we can do to simplify it. So let's take a look. Let me give this a little bit more space. It's going to require a nice amount of writing. There we go. Got this guy too. Okay, so negative 3x times the square root of 12x. Okay, the square root of 12x is the same thing as saying negative 3x. Now let's take a look at the square root of 12. What do we think about in terms of perfect square factors of 12? Can we simplify that? So I'm just going to break this up. Square root of 12 times the square root of x. So 12, 1 and 12, 2 and 6, 3 and 4. 4 is a perfect square factor, so we can rewrite it like this. Negative 3x times the square root of 4 times the square root of 3 times the square root of x. Now remember, with the square root of x, we only have one factor of it. There's a little 2 on the outside and a 1 on the inside. We can't simplify it. You can only simplify it if your exponent is greater than or equal to the index, and it's not. So that x is going to stay on the inside of the radical. What we can do is this. The square root of 4 is 2, and then square root of 3x. These guys are left over inside the radical. So this first term reduces down to negative 6x times the square root of 3x. Well, let's take a look at these next two terms and see what we can do in terms of simplifying them. We have 5 times the square root of 27x cubed. I'm going to rewrite it over here. So 5 square root of 27x cubed. Okay, so we can rewrite this as 5. Now, let's think about the square root of 27. Let's think about all the factors of 27. We have 1, 27, 2, we have 3, and 9, 4, 5, 6, 7, 8. They don't go into it. And look, after a while, you don't have to write these down. Sometimes these numbers will just pop right into your head, but I'm going to write them down for those of you that are interested in seeing them. Any perfect square factors? Sure. 9 is a perfect square factor, 27. So we can rewrite this as the square root of 9 times the square root of 3. And I'm going to call that times the square root of x cubed over here. All right, so let's simplify this bit. So square root of 9 is 3, right? We have a square root of 3 left over on the inside of the radical. And that guy, this is equal to 3. This guy's going to stay over here on the inside of the radical. Now for the square root of x cubed, that you can simplify. Remember, there's a hidden index of a 2 and there's an exponent of a 3. And to simplify variables and exponents of this form, remember you say to yourself, how many times does 2 go into 3, or what's 3 divided by 2? And 3 divided by 2 is 1. So there's one factor of x that's going to be on the outside of the radical. And there's one x left over. So there's one factor of x that's left on the inside of the radical. Right, one more time, the square root of x cubed. 3 divided by 2 is 1. So there's one factor of x on the outside of the radical, and we have a remainder of 1 on the inside of the radical. And when we multiply these guys together, we get plus 15x square root of 3x. Okay, so that's that middle term. Last term, minus 7x square root of 3x. Nothing we can do with that guy. The minus 7x square root of 3x, there's nothing we can do with that guy. Notice, please, that 3 and x, there's only one factor of x. There's an index of 2, so you can't pull out any x's. The exponent's smaller than the index. And 3 is prime, so 3 is not going to have any perfect square factors. But also see, look, all of these radicals, all these indexes, square root, they're all the same. So that means that we can combine all of these guys down into, well, let's see. So remember that we're never going to touch, under addition and subtraction, we're never going to touch the radical. The radicand and the index are going to stay the same, but now what we need to do is we need to combine the coefficients of each one of those. And we have to be careful. These guys have to be like terms too, and they are, right? They're all x's. Negative 6x plus 15x minus 7x. All of these guys are like terms. So negative 6 plus 15, that's 9x. 9x minus 7x gives us 2x. So the answer to this guy is 2x times the square root of 3x. Okay, 2 more examples? Yeah, 2 more examples. All right, let's break each one of these up. There's a decent amount of simplifying in these, right? I mean, pretty much what we're asking you to do, that's the hardest part of these guys, is just making sure that you're comfortable with simplifying it. Let's use a fancy gold pen over here, I like that. So I'm just gonna put this guy off to the side. We have 5ab times the cube root of 54a to the 4th. Let's talk about what we can do to break this up. So I'm just going to rewrite the 5ab. That's on the outside of the radical, so we don't have to worry about simplifying it. Let's take a look at the cube root of 54, and then let's take a look at the cube root of a to the 4th. Cube root of 54. Does 54 have any perfect cube factors? Ooh, let's see. Well, 54 is 1 and 54. 54 is 2 and 27. 54 is 3 and 18. 4 does not go into 54. 5 does not. 54 is 6 and 9. Okay. Any perfect cube factors, it's a cube root. And notice we do. We have 27. So we can break this up into 5ab cube root of 27 times the cube root of 2. Now, what does that give us? That gives us 5ab. The cube root of 27 is 3. With a cube root of 2 left over, there's nothing we can do with that. Now let's take a look at the cube root of a to the 4th. Well, remember that, again, the exponent is greater than or equal to the index, so we can simplify that. And we know that 3 goes into 4 one time, or 4 divided by 3 is 1. We have one full factor of a. And then there's going to be one factor of a left over. right? 4 divided by 3 is 1 with a remainder of 1. So 1 factor of a comes out and 1 factor of a goes in. So what does this mean? Well, when we multiply these together, this is 5ab times 3a. Well, 5 times 3 is 15. This pen isn't showing up very well, sorry about that. 5 times 3 is 15. A times a is a squared. B times the cube root of 2a. That's what that first term looks like. So we're hoping to get a cube root of 2a on this guy too, and that's going to tell us something about if we could simplify it or not. So let's see what we get on that next guy. So let's move, we have 12 times the cube root of 2a to the 7th b cubed. Okay, 12, cube root of 2. Cube root of a to the 7th, I'm gonna do it like this. Cube root of b cubed. Okay, so 12 is here. Cube root of 2, we can't simplify that. We only have 1 factor of 2, right? That's the same thing as saying 2 to the first. So we're gonna leave the 2 on the inside. The cube root of a to the 7th. Well, 3 goes into 7 2 times. 7 divided by 3 is 2. And there's a remainder of 1. So, and again, another way for you to think about this is a to the 7/3, you put it in rational exponential form, and that's the same thing as saying a to the 2 1/3. So 2 complete factors of a, that's on the outside, and a to the 1/3 power, the cube root of a, is left over on the inside. And now for the last term, the cube root of b cubed, well, that value is b. 3 goes into 3 one time with no remainder, so we don't have a remainder there. So plus 12, a squared b cube root 2a. Okay, what do you think? What do you think? What do you think? Let's see what we have here. Well, we have 2a, we have cube root. So it looks like we'll be able to combine them, but again, notice we're left with kind of polynomial terms on the outside. We have to make sure they're like too. We have a squared b, we have a squared b, so they are like, we can combine them. So what that means is we're gonna be left with the cube root of 2a, 5a squared b plus 12a squared b is the same thing as saying 27a squared b. So the answer to this guy simplified completely is 27a squared b times the cube root of 2a. Okay, we're doing one more. Last one. Let's take a look at this last one. How about you do this? How about you pause the video right now and see what you can do in terms of just simplifying the radicals completely. So take a look at all 3 of these radical terms and see what you can do in terms of simplifying these radicals completely. Okay, welcome back. Let's make some space here for this guy. It's gonna take a little bit of work to write this guy out here. Okay, so we have 4x times the square root of 32y to the 5th. Let me just separate, I'll put my work over here. So 4x square root of 32 square root of y to the 5th. Okay, does 32 have any perfect square factors? 32 actually has a few perfect square factors, but remember we talked about this idea that if you have a number with a few perfect square factors, you really want to go for the biggest one. And the biggest perfect square factor of 32 is 16. So we're going to break this up. We're going to call this 4x square root of 16 square root of 2. And now when we go to simplify that, that gives us 4x square root of 16 is 4 times the square root of 2. Now let's look at the square root of y to the 5th. So remember, there's a little hidden 2. 5 is bigger than 2, so we can simplify it. So we know that 2 goes into 5 2 times, or 5 divided by 2 is 2 full factors, and there's a remainder of 1. Okay, so when we multiply these two together, 4 times 4 is 16, x y squared, square root of 2y. That's the first term. Let's see what we can do with the second term. Negative 5y squared, square root of 72, x squared y. I might need another page for this, sorry. Oh, it's not letting me. Okay, that's okay. We'll stay here unless we have to move. Okay, so -5 y squared, square root of 72. I'm just going to break this up initially into their different factors. Square root of x squared, square root of y. Okay, let's start with 72. Okay, lots of factors of 72. Remember, we have 3 different perfect square factors, so the biggest one is going to be over here. It's 36. Once you hit that biggest one, if you want to end it there, you can. So that means we can rewrite this as -5 y squared, square root of 36, square root of 2. And I'll hold off on these guys for a second. So that's -5 y squared times 6. Right, that guy is equal to 6. Square root of 2 left over here, that's this guy. Now the square root of x squared, well, that can be simplified. We have the same exponent, the same index. 2 divided by 2 is 1 with no remainder. And then a y left over on the inside of the radical. So what are we left with? Well, on the outside, -5 times 6 is -30. Y squared x, xy squared or y squared x, the order isn't important, and a radical 2y left over. Let's compare that with the last term. Oh man, I don't need any more of that. 8xy squared, square root of 2y. The square root of 2y cannot be simplified, so I'm just going to recopy that guy, right? 2 is prime. Y, we only have one factor of it, so there's nothing we can do with that. So that's just going to be plus 8xy squared, square root of 2y. All right, so what do we see? I hope you see it. We see this. We see now the radicals are the same. Notice also this is a fairly decent sized polynomial, 16xy squared minus 30xy squared plus 8xy squared. And they're like terms. They have to be like terms for you to be able to combine them together. So we have 16xy squared minus 30xy squared plus 8xy squared, and 16 minus 30 is -14. -14 plus 8 gives us -6. So the answer to this guy simplified completely is -6xy squared. I always enjoy adding and subtracting radicals, so I hope that you've enjoyed it as well. These are my hearts. This is my heart-shaped flower. What I'm going to do is I am going to put an HW on HW. Okay, so you guys are finished with this section. Go off and do your homework now for adding and subtracting radicals.